Okay, so we've just about got out of time for snow, but who knows? We might have one more. But it doesn't matter what we want at all. So next time that it does snow and you're pulling your sled, you may want to think about your most optimal sled pulling angles, because as you pull your sled, okay, as you pull your sled, you will be exerting a force upon the string, right? And that string will pull the sled. But you really only want the sled to go in this direction, right? You don't really want to pull up on the sled at all. However, it would be rather inconvenient to pull the string at a level perfectly level with the sled, right? Because if you do that, you're going to have to crawl on the ground to do that. So I don't think that would be ideal. But this particular person, they are pulling their sled, I really should have drawn it a little steeper there, at an angle of 62 degrees with the ground. And they are exerting a force of 4 newtons on the string. Okay, so that vector right there, that 4 newtons, is right there. And that's the force on the string. Okay, so we want to know the horizontal and the vertical components of the force. And this is still one of the easier problems that we'll have here. So our horizontal force would be, I'm going to call this right here X. And then our vertical force, if we drew this here, we'll call that Y. Right, and we could make ourselves a little parallelogram here. Alright, and we know the hypotenuse. We know that hypotenuse, that force that's exerted on the string, that's 4. So this problem is a lot like the problem where we had the different directions of the wind. So we need to say, in this case, if we're looking for X right here, this is a right triangle, and to look for X, we would have the adjacent side and the hypotenuse. For adjacent and opposite, or adjacent and hypotenuse, we use cosine, right? Because cosine theta is adjacent over hypotenuse. So looking down here, we would have cosine of our theta, our angle is 62 degrees, equals the adjacent, which is our X, over the hypotenuse, which is 4. Okay, to solve that, we just have to multiply both sides by 4. So cosine 62 is going to give us that X equals, I bet this is in radian mode. No, in degree. Oh, 1.878. And I was thinking that was wrong because I was thinking of angles, but this is not an angle, that's newtons. Right. Okay. So the force that is actually pulling the sled is only 1.878 newtons. That's your horizontal force. Right? Basically, any upward force that you have is sort of wasted, right? Because you don't want to pull your sled, assuming you're pulling your sled along level ground. It makes it a more complicated problem if we're pulling the sled up a hill. Well, we're just dragging our sled across the yard to go get to the hill, I guess. right now. So we can make this a more complicated problem, which we're going to do later. I actually don't have any sled problems, but we could do this later, where we could be pulling the sled back up the hill, and then we won't have a right triangle anymore if we do that. So 1.878 newtons of force is actually being used. The other part, at this point, you could use Pythagorean theorem if you want, or you can use trig. I'm just going to use trig. So the y is the same as over here. So you're going to have sine of 62 equals y over 4. To solve that, you'll multiply both sides by 4. So if you do 4 sine of 62, you get y equals 3.532 newtons. And this, I'm going to call this is our horizontal, and this is our vertical. I really should have drawn that better to scale because it doesn't look correct, but really a 62-degree angle, here's our ground, a 62-degree angle would be more like this. So you'd have the vertical portion here and the horizontal portion. Like that. Alright, so that would be more drawn to scale. So, so in this case, all of this force is more or less wasted because it's not actually pulling the sled forward. This force is what's actually doing the work that you're wanting to accomplish. So, if you wanted to be more efficient, what could you do? What's that? Lower your string, right? So 62 degrees is a pretty high angle. If you hold your string down lower, then that would make you more efficient. Although, eventually you're going to have to like bend over, and that's going to hurt your back and probably not be ideal either. So you could sort of figure out, depending on your height and your range of motion, I guess we could say, length of your arms, what would be ideal for that. If you're pulling the sled up the hill, things change differently. We need to do a problem like that. That would actually be an interesting problem. But right now I don't have one. Okay, so let's see. Okay, yes, we definitely need to do this one. So 7. Here's where we get into some different stuff. So vector A, these are just regular vectors. We have no application here. Vector A has a magnitude of 3 and a direction of 0 degrees. So I'm going to draw this first vector. It has a magnitude of 3. So actually, it might be in our best interest. I think we'll be okay on this one. Next one I might need to draw a scale. Alright, so we have a magnitude of 3, and then vector B has a direction of 50 degrees and a magnitude of 4. Make this a little bit bigger. 3. And then vector B has a direction of 50 degrees and a magnitude of 4, so it's a little bit longer here. And we know that this angle right here is 50 degrees. This side right here is 3 centimeters, and this is 4 centimeters. Now, remember, when we're doing this, we've got to make a parallelogram, right? So we're going to draw a parallel line right here, draw a parallel line right here, and our resultant vector goes from the starting point to the other side of the parallelogram. We would also know if this is 4, this is 4, this is 3, this is 3. Alright, so here's our problem for this. I do not have a right triangle here. Okay, so the problems that we've been doing so far, we've all had right triangles. We could do Pythagorean theorem, we could do sine, cosine, or tangent, we could find what we needed. But I don't have a right triangle here. So I cannot do Pythagorean theorem. I also cannot do regular trig. So for this, we're going to have to use law of sines or law of cosines. The other problem that we have here is I don't have any angles. What I need to do is I need to look at maybe like this triangle, or I could look at the top triangle. But I need to look at one of those triangles. I know this side is 3, I know this side is 4, but I don't have any of the angles. There is a property of parallelograms that I don't know, you guys may not have learned it because they destroy geometry these days with Math 1, 2, and 3. But there's a property of parallelograms that tells us that this angle and this angle, consecutive angles in a parallelogram, have a certain property. Does anybody know what that is? Okay, you probably haven't learned it. So if you have parallel lines, and this would be in math too. If you have parallel lines, these two angles right here, those are called consecutive interior angles. You learned other things like alternate interior, alternate exterior. You remember hearing those sort of things. What do you know about consecutive interior angles? Do they look the same? No, they're not the same. We can't always assume that, but they're not. They add up to 180. Consecutive interior angles add up to 180. The angles that would be the same, Justice, there are some that would be the same, like this angle and this angle right here, those would be the same. And so since like this angle is the same as this one, and those two make a line, it has to add up to 180. So the consecutive interior angles in a parallelogram have to add up to 180. So that tells me if this angle right here is 50, what's this angle right here have to be? 130. So that is an essential property for you to know to be able to do these problems. Now, if this is 130, this angle is 3, this side is 3, this side is 4, I can use law of cosines to solve this problem. Okay? So if I call this side right here, the length of that vector, if I call that x, then I'm going to have x squared equals 3 squared plus 4 squared minus 2 times 3 times 4 cosine of 130. And so if we grab our calculators, 9 plus 16, well, I don't know what I'm doing now on the calculator. We end up, oh wait, we can do the whole thing. Let's see. Hello. You're welcome. Okay, and so we get 40.427, and we are going to square root both sides of that. And whenever you do that, you get 6.358. And they measured these in centimeters, so that's going to be centimeters. There. I'm going to go ahead and store this as x. There's one other thing I've got to find, so I'll store it just in case I need that number. Okay, store is right above the on button, so you just hit STO and then whatever letter you want to store it as. Store, this button right here above on is your store button. So when you got that number up, just hit STO, and it'll say answer and a little arrow, and then type whatever letter, so alpha and whatever letter you want to store it as. case I just did an X. Okay. Okay? A lot of unnecessary. Okay. Any questions so far? All right. Now, we've got to find the direction. The direction, whenever problems are given like this, and they're not telling you north, south, east, west, the direction always begins right here on the positive part of the x-axis, and it goes up to whatever vector you're looking at. So we're looking at this angle right here. I'm going to call it theta. You call it whatever you want. So if I want to find that angle, that would be my direction here. Then now what I'm going to need to do is use law of sines. Okay, I just found x, so I could say that sine of 130 over the x that I just found, which is 6.358, but I'm going to use that value I stored in my calculator, equals sine of theta over, Nathan, which side do we have across from our theta here? If we're looking at this triangle, the fourth. Okay? Alright, now we've got to solve for that theta, so we're going to cross multiply. So we get 6.358 sine theta equals 4 sine 130 and divide by 6.358. Now notice when I type this in, I'm going to do 4 sine 130, and then I'm going to divide it, rather than 6.358, I'm going to divide it by that x that I stored in my calculator, because that way I won't round any for this, so I get 0.48192. And then, what's the last step you're going to do for this? Inverse sine. So theta is going to equal inverse sine of this answer. Okay, so we get 28.811 degrees. So our magnitude is here, the 6.358. Our direction is 28.811. The problem did not have north, south, east, or west, so you don't have to put north, south, east, or west with your answer. Okay, questions? Okay, here's our next one. Okay, so this gets us to what is probably a little bit more realistic of an airplane problem, because in this case, we've got the wind, rather than blowing perfectly in one direction, the wind's blowing 20 degrees north of west. We're even going to see some eventually where the plane's not going perfectly west. The plane might be going south of east, and the wind is blowing north of west, and we've got to figure out what happens there. So, so we're going to start this. Let's see. Airplane is flying due west at a velocity of 120 meters per second. The wind is blowing 20 degrees north of west at 15 meters per second. What is the magnitude and direction of the plane's resultant velocity? So, north and west are the directions we need the most of here. So, I'll draw my axis like this, and north, south, west, east. And our airplane is flying to the west. So our airplane is flying to the west, like this. Hold on, that to be vector. And then our wind is blowing 20 degrees north of west. So I know that's going to go like this direction. Is the 20 degrees going to be the angle sort of down here, or is it going to be the angle over here? The bottom one or the top one? Okay, north of west. So which side does it touch? It touches west, right? So it's north of west. So it's going to touch west, which means that your angle is going to look like this. Okay? And that 20 degrees is going to be right here. And so our magnitude here is 120. Our magnitude here is 15. We've got to make a parallelogram. And then our resultant velocity is going to be from our starting point to the other side of our parallelogram here. Now, I didn't exactly draw this to scale. In fact, if I actually drew it to scale, it would probably be even skinnier of a triangle. Sometimes I don't like this whenever it makes this really like tiny triangle. So I know this side is 15. What would this obtuse angle right here be? 160, because this angle and the 20 degree angle over here for that parallelogram, they have to add up to 180. So this angle right here is 160. Sometimes I like to do this. I like to make this look like a much bigger triangle. Like this, I can see it. This is 120. This is 15. This is 160 degrees. And so the first thing we're going to look for is that magnitude of that vector. Okay, law of cosines again here. So we're going to have x squared equals 15 squared plus 120 squared minus 4 times 15 times 120. Cosine 160 is 2. Thank you. I think I've been doing quadratic formula with my Math 1 kids and things are getting mixed up. And so our x squared, we're going to have 15 squared plus 120 squared minus 2 times 15 times 120 cosine 160. And so we get this number for our x squared. We got to take the square root of that. And we're going to get x equals 134.193. And that's going to be in meters per second. And it should make sense. It should be a little bit faster than either the plane or the wind by itself there, but it should be less than 135 because it's not just both of them in the same direction. Okay, question on that part? Alright, so then we have to find our direction. So the wind is blowing at 20 degrees north of west, but it's not nearly as strong as the velocity of the plane, right? So it's going to throw the plane off course, but only by this really small angle right here. So if I call that theta right there, that would be this angle right here. And we have to remember, like, this angle is 20, but that one does not necessarily cut it in half or do anything special there. We've got to use some trig to figure out what that angle right there is. So we just found x, so we can do sine of the x, sine of 160 over that x. Actually, before I do anything, let me store that x. So store that is x, so I don't have to round it off. So over 134.193 equals sine of theta over 15. We will cross multiply here. So 134.193 sine theta equals 15 sine 160. Got to divide by 134.193. So sine theta is going to be 0.03823. And if we do sine inverse, we're going to get theta equals 2.191 degrees. And what direction is that? North of east. It is west, sorry. North of west. Yes. This, in the parallelogram, 20 degrees is like, so for, like, let me do this right here. Before you draw in the resultant vector at all, you just have this parallelogram, right? So whenever we draw in that vector right there, the angle right here is going to be north of west. So like this angle, it touches west and goes to the north of that. So that is the angle of the parallelogram. But when we draw our resultant vector in, there, when we draw that resultant vector in, that angle right there is not 20 anymore because it cuts it like small. In this case, yes, because your angle needs to touch north, south, east, or west. And in this case, the only angle that does that in that parallel, in that triangle, is this bottom angle. Like if I found instead, if I used this triangle and found this angle, that angle does not touch north or south, or east or west. So, I mean, you could find that angle if you want, but you'd end up having to subtract it from 20 and finding this angle in the end. Because whatever angle you end up finding has to touch north, south, east, or west when you're doing a problem like this. Does that answer your question? Okay. All right. Questions? Okay. Here is our last one that we're going to do. So vector A has a magnitude of 3 feet and a direction of 20 degrees. Vector B has a magnitude of 100 feet and a direction of 200 degrees. Find the magnitude and direction of A plus B. So this one, for this problem, we are not doing north, south, east, or west. We are thinking of, done unit circle, we're thinking like unit circle values. When we have a direction of 20 degrees and a vector of 3, that will look something like this right here, where this angle right here is 20 degrees. Then for 200 degrees, we would start right here on the positive x-axis, and we've got to go counterclockwise 200 degrees. How far is it to get all the way around here to the, that's 180, right? So we'd have to go 20 degrees past that which means our second vector would look this longer. It would look like this. And so that angle right here all the way around, that's 200 degrees. But this little angle right here, we said that was 20 degrees. And this is 3. And this is 10. So, how are we going to draw a triangle for this, or a parallelogram? You really can't in this case, right? Because here what you got, these two are going to make a line, a 180 degree line, because if you take 200 subtract 20, you get 180 degrees. They're opposite of each other, right? So in this case, you can't draw a parallelogram because all you have is a straight line. So what you need to do right here is just think of it as like a tug-of-war match. If I have Caroline and Jaden over here in tug-of-war, and she has a force of 3 newtons in this direction, and Jaden has a force of 10 newtons in this direction, Jaden's going to win, right? And he is going to pull Caroline in his direction, right? With a force of 7 newtons, because he is stronger than she is, right? So if your forces are opposite each other, you're just going to subtract them. So 10 feet minus 3 feet gives you 7 feet. So that's the magnitude of your vector. And it's going to go the direction of whichever force or whichever vector is longer here. So that's going to be 200 degree direction. So if you ever get any of these where they're exactly opposite of each other, you're just going to subtract them and they go whatever direction the strongest wind. So if you have a wind blowing north at 20 miles an hour and a wind blowing south at 10 miles per hour and they intersect, it's going to end up being a wind blowing north 10 miles an hour, right? Whichever one's strongest wins out by whatever amount is stronger than. Okay? All right, so